Hello everyone. Good morning, afternoon, evening. Dear authors and invited guests, welcome to technical session 5C. Myself, Vidhi Rangdale, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Congress on Information and Communication Technology, that is ICICT 2026, London, UK. The 11th edition of the conference is being organized in a hybrid mode. The physical event was held yesterday in London, UK, and the virtual event is being held through Zoom from 25th to 27th February 2026. I hope you will enjoy the knowledgeable and interactive sessions throughout the day. In this session, we have 6 presentations. Each presenter will be given 12 minutes for the presentations and 3 minutes for question and answers. On 10 minutes, I will raise a gentle reminder. There is another request to all the participants that you all stay connected with us till the closing remarks. If you have any query or update, then you can write it to me in chat box. Just before we start the session, I would like to introduce you all to the chair for this session. We have Dr. M.F. Mrida and Dr. Vijay Mani as our session chair. Dr. M.F. Mrida, senior member of IEEE, is currently working as an associate professor in the Department of Computer Science at American International University, Bangladesh, that is AIUB. He is the founding director of Advanced Machine Learning, that is AIML lab at BUBT. His research interests include artificial intelligence, that is AI, machine learning, deep learning, and natural language processing, that is NLP. His research expertise within both academia and industry results in over 120 journal and conference publications. We also have with us our second session chair member, Dr. Vijay Mani. Dr. Vijay Mani is the Dean of Alumni and Outreach at Vishwakarma Institute of Technology, Pune, India. With 24 years of teaching and 2 years of industry experience, he brings deep expertise in biomedical engineering, IoT, and image processing. His research contributions include over 60 published papers and 17 patents, reflecting his commitment to innovation and academic excellence. We welcome you, sirs.
Thank you, Vidhi.
Now, I would like to start with the paper presentations. I would like to invite Jenny Marcela Sanchez Torres to present a paper on a systematic review of models for measuring algorithmic governmentability.
Hi, Betty Guam. Let me share the screen, please. Sorry. Huh? I think that I have a problem with my camera. Okay, well, let me share. So I prefer to okay. Can you see the presentation now? Could you tell
Yes,
me,
we
please?
can see your presentation.
Okay, thank you very much.
Actually, your screen is visible, not the presentation.
No?
No.
Okay, stop share. This one. Okay. Now? Yeah.
It is visible now.
Okay. Okay, thank you. So I'm sorry, but my camera doesn't work. I don't know why. Well, good afternoon, everyone. My name is Marcela Sanchez Torres. I am full-time professor at the Universidad Nacional de Colombia. Today, I will present the findings of a systematic literature review on models for measuring algorithmic governmentality. This study was conducted as part of my sabbatical research project with the academic support of Professor Giraldo Rios. Let me outline the agenda of my presentation. Sorry. I'll begin by introducing the background and purpose of this research. Then I'll explain the methodological approach. Finally, I will share the main findings and conclude with their implications. The central concept of this study is algorithmic governmentality, hereafter referred to as AG. AG denotes a mode of governance in which algorithm systems process large-scale data to inform, guide, and sometimes automate public decision-making. While related to digital government and digital governance, AG specifically emphasizes data-driven regulation and the exercise of the power through algorithmic logic, predictive analytics, and artificial intelligence in the public sector. This transformation generates both opportunities and risks. As you see in the slide, on the one hand, algorithmic systems can improve administrative efficiency, optimize resource allocation. They can also increase transparency, reduce arbitrary discretion, and enable more personalized public services. On the other hand, challenges persist. The reduction of human discretion may weaken contextual judgment, accountability can become unclear, and biased data sets risks reproducing systematic inequalities. Algorithmic opacity foster black box decision-making, undermine public trust, while intensified datification raises concerns related to privacy and surveillance. In this context, understanding how algorithmic systems are evaluated and governed has thus become a priority for ensuring public trust in AI-driven governance. This study therefore addresses the following research question: how have existing models, methods, and frameworks related AG? In consequence, the aim of this paper is to analyze how AG has been measured and evaluated across different contexts through a systematic literature review, which was designed in 3 phases. First, we formulate guiding questions focused on the temporal evolution, structural characteristics, and functional purposes of existing models. Then we design a search strategy combining keywords related to AG, algorithmic governance, regulation, and measuring across academic databases, covering a 20-year period from 1990 to 2095. The initial search gave 100 records after duplicate removal. Following a systematic full text analysis, 15 studies met the criteria for in-depth examination. Those 15 studies describe 52 different models. Finally, we developed an analytical template to extract and compare attributes across the models. Applying the method, I will present the analysis of the 52 models into 4 aspects: a general overview, a taxonomy of model categories, a comparison of dimensions, variables, and indicators, and a review of the methodological approach employed. Regarding the general overview, we identified 32 models, which can be grouped into main categories. 70 correspond to conceptual foundations, focused on theoretical reflection rather than operational implementation. The remaining 15 are standalone assessment tools that integrate measurable indicators and multidimensional evaluation mechanisms. From a geographical standpoint, half of the models are from European countries, indicating a strong regulatory and institutional drive in that region. In contrast, the Global South remains underrepresented due to resources limitation, insufficient technical, and fragmented or immature regulatory environments. These findings suggest not only a methodological gap, but a geopolitical asymmetry in the production of AG measurement models. This study reveals that identified models can also be grouped into 4 analytical categories, which make up a proposed taxonomy. And a model can belong to several of these categories. The results show a predominance of ethical regulatory frameworks comprising 31 models, followed by participatory governance models, approaches with 29 models, reflecting an emphasis on transparency and citizens' engagement. Technical validation models account for 23 models, reflecting institutional priorities related to robustness, reliability, and performance. In contrast, human-centered and social impact models are represented with 17 models indicating limited attention to user agency and social cultural factors. The predominance of certain models categories also carries implications for public policy. Ethical, regulatory, and technical validation models reinforce legitimacy through compliance. Participatory governance models promote inclusion by incorporating citizen oversight, while human-centered approach emphasize social and distributed impacts. Regarding to the comparison of dimensions, variables, and indicators, the quantitative mapping reveals a clear structural gap of 170 measuring entries. Only 36 correspond to operational indicators, while 134 remain at the conceptual level. This highlights a key challenges. Although many frameworks define relevant evaluations dimensions, few translate them into standardized, reproducible, and policy-ready metrics. Developing harmonized indicators would improve cross-jurisdictional comparability, support evidence-based regulation, and strengthen public trust in AG governance. The analysis also shows that measuring efforts are concentrated in a few areas. Technical robustness dominates with 42 mentions, followed by transparency with 30, while stakeholder engagement and risks and governance receive less attention. Regarding to the methodological approaches, the figure shows that the mixed methods approach dominates, combining qualitative and quantitative evidence. Qualitative methodologies remain central worldwide, highlighting the interpretative orientation in this field. In contrast, quantitative models are scarce, which suggests that standardized and operational indicators for assessing AG are still underdeveloped. As illustrated in the figure, Europe leads both conceptually and empirical, while the global south remains underrepresented. This imbalance highlights the need to stress methodological diversity, expand empirical validation, and foster cross-regional collaboration to build a more inclusive and globally representative framework for assessing AG and its governance. Moving from the results to the conclusion, despite the fact that there is a small number of studies reported in the literature, we can conclude that the field of AG assessment is clearly developing, with Europe and North America leading. However, our analysis reveals significant methodological gaps, including excessive reliance on qualitative methods, weak empirical validation, limited geographical representation, and insufficient focus on user-centered and social cultural dimensions. To address these challenges, we propose 5 recommendations. First, standardized and broadened assessments indicators to cover both technical performance and human experience. Second, prioritize mixed methods approaches to combine qualitative and quantitative evidence. Third, strengthen geographic and cultural inclusivity through collaboration with underrepresented regions. Fourth, adopt life cycle-based governance models to enhance transparency from design to evaluation. And fifth, reinforce institutional capacity by equipping public organizations with the necessary tools, expertise, and also training. Sorry. future research directions should emphasize case study, participatory validation, and real-world testing to strengthen empirical and democratic foundations. Thank you very much for your attention. These are the references that we have used in this presentation, and this is our context. Thank you very much.
I request the session chair for questions and answers.
Okay. Yeah, this was a good presentation. I just have one question. So, what is the next, you can say, plan for this? Are you going to implement this in any application or the purpose? Am I audible?
Could you repeat?
Yeah. What is the purpose of this study? What was the purpose of this study? And are you going to implement anything out of this?
The main purpose in that case is because I live in Colombia, and our government are doing a regulatory framework for AG. Yeah, so we need to because they try to copy and paste the European regulatory in the country. So for us, it's quite different because we start in different level. Of course, we although we have 50 years of experience in the country developing in artificial intelligence, we don't have the infrastructure, we don't have the skills broaden in the population to create AI systems. Yeah, by inside in the government, they also using AI systems to decision making since 15 years ago. And now the government planning or are developing the main regulatory for using the AI, including the educational and the public services. So there are a lot of worries about that, and we need to establish what are the models that everyone uses around the world to evaluate those systems. And this is the main purpose to try to build an framework based in our context. So that is necessary to check to do the review around the world. That's the purpose.
Okay, thank you.
Thank you.
Hello?
Hello.
Yeah, could you tell
Sorry.
me is it possible to give me the example of how standardization can be operationalized in this context?
Could you repeat, please?
Could you tell me the example of how standardization can be operationalized in your context?
Okay. For instance, we found out some variables that you can use many indicators for evaluate that variable. Yeah. So we need to define special indicators that or clearly indicators for the decision maker policers. So for instance, in a special AI system for answering FAQ, yeah, frequent answer questions, yeah. How many people are satisfied for the answer of the AI system? But this kind of indicators are different in depends on the AI system. So we need to define broad indicators that the public, I mean, the making decision person can use for that purpose. That to measure that the AI system really answers or really responds to the public value that it was made.
Okay, thank you very much.
Thank you. Is there any question?
You can go for next presentation, Vidhi.
Okay, thank you.
Yes, sir. We now invite Durga R to present their paper titled Advanced Anomaly Detection Techniques for Water Quality Monitoring, Implementation and Evaluation using Physiochemical Datasets.
Is the screen is shared? Could you hear me?
Yes, go
We
ahead.
can hear you.
Could you see my screen in a full screen format or?
It's full screen, ma'am.
In full screen? Shall I start then?
Yeah, please.
Yeah. Okay. So good afternoon. Myself, Dr. Durga Rajan from Capital City College, and my corresponding author is Dr. G. Kodai from SRM Institute. Good afternoon to one and all. My topic is on advanced anomaly detection techniques for water quality monitoring, implementation and evaluation using physicochemical data sets. So this is my agenda. Is of about introduction, literature survey, and then I'm going to talk about the architecture, and then experimental setup we are using, and then system implementation, and then comparison results, and then conclusion. Okay, introduction. So why we need to find the water quality monitoring by means of automated system is because the manual monitoring is very slow and requires a human people to visit the site and to get the readings, and it is not the time series data, since because it is taken by the human labor. And the testing frequency is also is a constraint, is a very important one, because it needs a human labor to be in that place and to get the data. So thereby is a need for automated system to overcome these limitations of the manual monitoring. So what is anomaly detection is like anomaly detection is to find the anomalies like data points which is from the water to measure the quality of the data, so that the learning patterns in the water quality data can be collected in the format of timely series. So you by detect the abnormal behavior, thereby we can stop any kind of hike in the kind of chlorines or the temperature. There will be abnormal changes can be happen at any time. So with the automatic detection, and that's called as the we using the automatic detection, that which identifies the deviations from the normal operation. So evaluation of detection methods, we are using, these are the major categorical methods to know about the automated of checking the anomaly detection in the water quality. The first one is a statistical method. The second one is machine learning. And sometimes we do hybrid approaches nowadays. The statistical method approaches are two methods which we used to be look on a statistics manner. So is a Z code and then a monopoly distance prediction, where this is a statistical method and machine learning approach, which can be done automatically in a real time. It collects the data in a time series. And then hybrid approach, which combines the statistical method and the machine learning approach, thereby it increases the optimum results. So these are the addresses. We need to address the limitations. Because of the statistical method, it will be good for the smaller data set. And then machine learning, if it collects all the different types of attributes. In our work, we are using 9 attributes. Thereby, it could be able to find with the not a very big data set is a possible data set. And the hybrid approach, which could be very good for combining for the bigger data sets. So the study purpose is like the main objective of this particular study purpose is to understand or to describe and evaluate different learning algorithms for the water quality data analysis. So we just comparing those algorithms and identifying its strengths and weakness. And we are going to detect the detect in real time, and what are the possibilities of the changes and what is the accuracy of prediction either by among these 5 algorithms, which one compares with give you the best results. Right. So first is like a kind of a approach. These are the different types of approaches we use. The first one is a manual sampling. So the manual sampling, which has a kind of only limited spatial and temporal, and the coverage is very slow because we need to wait till the lab results from the human labor, and the data volume might be very small because a human can collect for a day kind of very small data. So the automation is manual because you need to reach to the lab and testify it and collect the results. Whereas by IoT sensors, it collects the data in a time series manner, and that in real time, the data is collected and it will be sent it to the lab by itself over that network. And it was automated, so you can able to predict the data quality for a particular time series. UV-VIS spectroscopy is a kind of a continuous coverage. It detects the quality of the data automatically in a very speeder time, and it automatically sends to the lab, and it will detects the results by itself. You don't want to wait until the lab results. It detects the data immediately. It's a kind of continuous flow. So these are the approaches it is the evolution of the water quality monitoring. So being the literature review, we compare these algorithms such as the statistical algorithms on Z-score and Mahaloban is algorithm, where machine learning we are using isolation forest and then SVM and then local outlier forest. So we are not doing with the deep learning, but it depends on the model size. Yes, the real time is deep learning is better with the comparative with the other algorithms. So this is the system architecture. We are using a 3-layer architecture. So the layer 1 is a sensor network layer, and layer 2 is a data processing layer, and then this is a decision-making algorithm layer. In the layer 1, we are using the sensor network, and in the layer 2, the data pre-processing is happening. And then the decision-making algorithms, here we are using the different types of 5 algorithms, but these 2 layers are going to be the same step across all the algorithms. In the sensor network, like real-time continuous monitoring of psychochemical parameters, which is observed directly from the water, and there is a transmission of data over the internet, and all the data has been collected in the cloud, and it receives the data from the nodes, and data validation and cleaning to the data cleaning might be happens because when you collect the data from the sensors, sometimes there will be power fluctuations. At that time, it couldn't able to collect the data. So if there is no data in the particular record, then the machine learning algorithm couldn't process that particular data. So we need to do the data pre-processing. And of course, time synchronization will be recorded with the every data collected. Initial threshold based on the anomaly detection, we are going to threshold based because all the data we do have the threshold. So if it is above the data, then we need to raise an immediate alarm. So this is our system architecture, where these sensors are in the water quality, where it collects the data once and while, and then the data is collected from the submerged water quality sensors, and it sends to the IoT network, where the network sends the data directly to the lab by means of this bridge using the gateway nodes. It will direct all the data direct to the cloud in a safety manner. Once it is done, this web or mobile app is the user end, where you can see as a dashboard of your data, so that you could control the data, or you could able to visit the data at any time. And if there is any fluctuations, it will directly send the again for the flow happens again and again. So this is how the architecture has been made. Right, so this is the experimental environment we used to implement this part. So we are using the Python and then intermediate code, and then this is the pandas that we are using as a part of the experiment. Right, so our data set consists of 3,276 samples with the 9 physiochemical parameters. And the final values are potable or not non-potable. So it is a 61% of non-potable and 39% of potable, because when you process the machine algorithm, it should be consist of 61. That way it could able to balance like those kind of stuff. Otherwise, it will keep on giving you the false positives. So there are 20 missing values. As I told you, it was a realistic or real world challenge. We are facing it. Sometimes there will be fluctuations. So this is how we split the data. We split the data across 80 for training and 20 for testing. So we preserve both on both the data sets. We consistently split across all the models because for the fair comparison, same pre-processing models is also we are applying for all the models. So this is how the system is implemented. We establish the processing to end-to-end anomaly detection. Data flows from the acquisition through pre-processing for the decision making. So once the decision, the real time is processed with a timestamp, and modular design allows algorithm update without disrupting the monitoring, because we are going to compare with all the algorithms. So as I told you, this is the implementation flow. We just for the pre-processing, we pre-process the data and clear the data, and we extract the features from the data and we classify it, and then we make the decision. So the classification and decision making is all based on the kind of algorithms we are going to compare. So for the comparison of algorithms, we first using the Z-score. The Z-score is a kind of the data which is far from the outlier. Then you'll rule it as that particular score is the anomaly. So we could able to find it. It works best when the feature is roughly kind of, and the features are treated independently. Where monopolis distance is a kind of a multi-feature version of the Z-score. It measures how far the point is from the center of data point of the water quality. So that's why it's all about the monopolis distances. So the local density for us is like global distance from the center. A point is an outlier from its neighborhood, which is much lesser than the neighborhood of the nearest neighbors. So this is one of the algorithm local outlier factor. We used it. And then isolation for us takes a different like kind of easy to isolate than the normal points. So it usually scales well and works nicely in the higher dimensions compared with the pure distance based methods. So last one is the one class SVM, which is a boundary based learning algorithm with the best in the future space. The label points are outside the boundary as anomalies. So are we comparing these 5 algorithms? So when we compare with this, a statistical method is a Z-score and monopolis distance, and machine learning algorithms are local outlier factor, isolation forest, and one class SVM. So from that, we could able to identify the ML methods are 72.7% higher recall than the statistical methods. Whereas the statistic method is is 15.1% higher precision on average, which is the best FN score, and then recall is given by the one class SVM machine learning method. But the Z score has the highest accuracy but lowest recall. So this is my comparison of all the algorithms, and this is my overall prediction from the algorithms of that particular data set. So I'm concluding that the algorithm selection highly depends on the operational context, or maybe a kind of what kind of environment you are going to use it on the particular water quality detection, or high precision methods for the cost sensitive environments. It all depends like based on what kind of environment, what kind of budget we do have, and what kind of method we are going to use. So I would suggest the future systems needs adaptability and scalability for the real world deployment. So in my future work, maybe I'll be work on the deep learning methods and to check how it be varies with the algorithm. And then I would just want to say thank you for all of you listening to my presentation.
I request session chair to ask questions and answers.
No question from my side.
Thank you so much, sir.
I have a question, if you don't mind.
Hi.
Dobby,
Oh, it's okay.
hello. Thank you very much
Hi.
for your presentation. I wanted to ask you, in real world scalability, how do you see this rolling out? Do you see it in sort of municipalities and water utilities, or in different environments, like say, for instance, fisheries? I'm just curious because I think it's got a lot of real world
Yeah,
applications.
you can apply this for the fisheries as because we work on the kind of different kinds of attributes. Say, for example, we are looking on temperature, pH, turbidity, conductivity, dissolved oxygen. Even you can find for the fishery, you can say the pressure of the water in the particular tank. If you're growing any kind of fishes in the house based or maybe commercial based, you have to check the pressure of the water. So if you want to know that pressure of the water is going up, then the fish cannot be stable inside. Or even in some of the fisheries, you could say the pH or the temperature need to be maintained for some kind of fishes, like which lives on different tropical zones. So if you fix the threshold for the particular water, and then it could keep on monitoring that particular threshold. If it is goes above the threshold, it could show you the kind of alarms, or it could show you the kind of in the user dashboards. So you could go and verify it. So you can implement these kind of small things in the, because it is a basic sensor nodes. You can buy it and you can install it and you can connect it over the IoT, and then you can create an app for it, and we can do it.
Thank you very much.
Thank you so much. Thank you for giving a time to present my presentation, and thank you all.
Good evening to everybody.
We now invite Komiljon Iminov to present their paper on artificial intelligence in dentistry and maxillofacial diagnostics, clinical applications of AI-based radiology and elastography. We are actually not able to hear you, Dr. Hamid. Are you trying to say something? Okay. Thank you.
Good evening, dear teachers. Today, you show my presentation, them artificial intelligence in dentistry and maxillofacial diagnostics. Clinical applications of artificial intelligence based radiology and elastography. Authors Shuhratbay Muradov, Kamiljon Iminov, Rudiva Sitora. Background and relevance. Artificial intelligence improves diagnostic accuracy, efficiency, and objectivity. Dentistry producing large volumes of imaging data, radiographs, cone beam computed tomography, ultrasound. Artificial intelligence enables automated image interpretation and dictation support. Early detections of caries, bone loss, and soft tissue pathology improves outcomes. Study aim and objectives. Evaluate clinical applications of artificial intelligence in dental radiology and elastography. compare diagnostic accuracy of artificial intelligence and clinicians, assess integration into clinical workflows, identify limitations and future directions of artificial intelligence in dentistry. Methodology: systematic review following PRISMA guidelines, databases PubMed, Scopus, IEEE, Explore, ACM, and period 2020 and 2025. 38 studies included five used for quantitative analysis. Evaluations metrics: sensitivity, specificity, and accuracy, AUC. Artificial intelligence and dental radiology. Analysis of intraoral radiographs, panoramic X-rays, and cone beam computed tomography. Convolutional neural networks trained on large datasets. Detections of caries, periapical lesions, and periodontal bone loss. Automated annotations and diagnostic results. So, diagnostic performance of artificial intelligence. Caries detection sensitivity 88%, specificity 90%, AUC 93%. Periapical lesion detections sensitivity 85%, specificity 93%, performance comparable or superior to extract clinicians. Artificial intelligence serves as reliable decision support tool. Artificial intelligence in ultrasound elastography. Quantitative assessment of tissue stiffness, differentiation of benign and malignant lesions, improved detections of tissue abnormalities, and promising but limited clinical validation. Common artificial intelligence errors and limitations. False positives due to anatomical variations and artifacts. False negatives in early or rare lesions. Need for human supervision and validation. Limited data sets and regulatory challenges. Integration into clinical workflow, patient examination and imaging acquisition, automated artificial intelligence analysis, clinician review of artificial intelligence findings, final diagnosis and treatment planning, improving efficiency and reduced diagnostic errors. Conclusion and future perspectives. Artificial intelligence enhances diagnostic consistency and early disease detections, supports personalized and predictive dentistry, requires clinical validation and ethical implementation. future data-driven and patient-centered oral health care. Thank you for your attention.
I request the session chair to ask questions and push answers.
Okay,
Class slide before this.
thank you.
Okay, we can go for next.
Yes, sir.
What? Sorry, repeat, please.
There are no questions. So we
Okay.
are to take the next presentation. Thank you. We now invite Noor Karim to present paper on authentication in Internet of Health Things ecosystem, an extensive review of challenges and countermeasures.
Good afternoon, everyone. Today, I will present my research titled Authentication in Internet of Health Things Ecosystems, an extensive review of challenge and countermeasures. Outlines introduction, IOHT, cyber attack and security issues, cybersecurity solution, authentication techniques, a look at authentication schemes, research gap in securing IOHT, conclusion, reference. Introduction. The rapid technological advancement have aligned the Internet of Things with the need of modern medical practice. Healthcare applications are now equipped with wearable, implantable, or bedside devices that collect patient physiological data through sensors, actuator, and biomedical systems. These devices are used for the diagnosis and treatment of patient. By exchange information among interconnected devices via the Internet. The Internet of Health Things can accurately monitoring patient and medical equipment and samples. The collected and analyzed data helps streamline the operation of hospital diagnostic centers and elderly care facilities. However, the publication of this system of our open communication channels leaves them vulnerable to numerous attacks and misuse. Sensors can exploit the data they collect, potentially putting patients at risk through unauthorized use of their sensitive health information. Confidentiality, non-reputation, data integrity, and device and user authentication have been recognized as key security requirements. In particular, authentication is crucial for fulfilling these security requirements as it identifies the identity involved in the system interactions. Internet of Health Things issues. Number one, communication of network network attacks. A denial of service attack prior to engaging in any resource intensive computation. We confirm message freshness and integrity utilizing timestamp and nonce. Each session will use a temporary ID and rapid hash-based verification to ensure the server is not being flooded by repeated legitimate or fake authentication requests. Some solution use a dynamic access control model that stop too many or duplicate requests and makes the system more stable against those attacks. Man-in-the-middle attack, a combination of certificate elliptic curve, Chinese reminder theory, NFTS, ASCON, hash function, and XOR can be used to prevent man-in-the-middle attack. Relay attack can be prevented by utilizing random integer secure session tokens and timestamp can prevent attacker from exploiting previously valid authentication data. Eavesdrop attack, this requires strong encryption using session key and algorithms such as AES and ECDH to prevent eavesdropping, along with secure authentication through certificate or tokens. Number two, cryptographic and key management attack. Session key disclosure attack. A session key disclosure attack can be prevented by forming a dynamic session key which is computed using new random values for every session and is not included in any authentication message. Session keys that are dynamically generated from several secrets, such as path-based secrets, server secrets, nonce, and timestamps. Number three, identity and authorized attack impersonation. Each legitimate entity authenticates with its partial private key and unique informal secret and distinct physical characteristic of IOHT devices prevent personal impersonation. Stolen verifier attack protocols can be designed or protocols can skip or reduce server verifier storage with paths securing data on devices and server against this attack. A privileged insider attack, passwords and biometric templates and are never sent in plain text. Passwords are secured with a one-way hash. Furthermore, healthcare organization must enforce strong security controls and risk management. Offline password guessing attack, ECC identity-based encryption helps protect against this attack. Symmetric encryption-based authentication prevents password guessing as access to the user secret key available from public or intercepted data is required. Look at authentication schemes. Modern IOHT security protocols use techniques such as physical and clonable function, BUF, elliptic curve cryptography, ECC, discrete logarithm problem, DLB, ASCON, and multi-factor monitoring to enhance security and reduce computational and communication cost. communication cost. Key advantage include protection against machine learning attacks, impersonation, stolen devices, and achieving accurate monitoring with high privacy. However, most protocol face limitation like stability issues, difficulty in parameter updates, reliance on key generation centers, and vulnerability to side channel physical attack. A research gap in securing IOHT. The heterogeneous components of an IOHT system communicate to enhance reliability, each adding security and privacy requirement for data protection. Even with dynamic algorithms and periodic key change, this adaptation alone cannot ensure storing security for IOHT systems. Due to limited computing power, memory, and energy, most IOHT devices cannot practically implement high complexity encryption and authentication. Centralized security model creates single points of failure and do not scale with more medical devices, highlighting the need for lightweight, scalable, and privacy preserving IOHT security architecture. Studies show that current IOHT security framework are insufficient due to device diversity, limited computing capacity, and lack of common policies or standards. Conclusion. This study highlights IOHT cybersecurity and privacy challenges mainly due to its integration with wearable sensor, implementable devices, and AI-based diagnostic tools, while enhancing healthcare, enabling real-time remote monitoring, and improving patient outcomes. This technology also creates numerous potential vulnerabilities for cyber attacks. This study outlines several security control, included encryption of all health-related data, strictly enforced access control, and high insurance levels for authentication to medical information that requires protection from threats such as DOS and data theft and unauthorized access. The article highlights the need for a lightweight IOHT cybersecurity framework to ensure authentication, data integrity, privacy, and compliance with health regulation and ethics. Thank you for your attention.
I asked the session chair to ask questions and answers.
No question with you from my side.
Thank you. Thank you for all.
Thank you. We will be moving on.
Thank
We now welcome Amelia Gonas-Melka to present her paper titled Developing an Ontology of Strategic Resources for Platform-Based Business Models Using the Business Model Canvas.
Thanks, Vidi.